Thank you all for coming. This is a honor to have you here. Thank you for the committee members, Professor Slovacki from GW, Professor Nadja Fizadeh, Professor Soljanin, and so Shoren. I should pronounce the Shoren if I should know.
It's cup, like the one you drink.
I'm using the Americanized. Anyway, so it's a pleasure of mine to have my student Morriel Kasher present. Well, hopefully he's going to pass. He's been working with me for a number of years, 7 years, six, 7 time passes. And it's a pleasure to have him present. He's been both undergrad and grad students with me. So this is his PhD dissertation. Welcome. Thank you.
Thank you. So yeah, as you heard, my name is Morriel. I'm going to walk you through some slides about the work that I've done over the past few years.
Sorry, we have another visitor here from another university, which is Professor Kokal Filipovic, and she was another PhD of student mine some years ago. She's at Rowan University.
Thank you all for coming. I really appreciate it, both virtual and in person. So the premise of my dissertation is fundamentally a study of quantization. And I think when a lot of people think about quantization, the first place they think about is compression of data that's already digitized. So classic example is image compression. We've all seen a JPEG compress a file pretty small, and any kind of lossy compression method has quantization at the heart of it. But another place where I think it's underutilized or maybe undervalued is in physical systems. So if you think about an audio processing system, lots of work goes into the analog side of the microphone, designing transducers and amplifiers and front-end components. But I think a lot of people forget that before we can do any kind of processing it with digitally, we've got to go through an ADC, which is an analog to digital converter. So this component is a fundamental gateway between the analog and digital world, and it shows up in basically every device that you would ever connect to a computer. One of the most important examples for us is actually in communication applications. So when it comes to RF devices, there's a huge amount of literature that describes in great detail how to design a front end, especially for these wideband systems with high rates. And there's plenty of literature on the digital side, designing optimal channel estimation algorithms and how to exploit and all of these different things. I think people, again, forget that the ADC lies in between, and it fundamentally limits the precision of our digital representation and therefore everything that we can do in the digital domain. So one of the places we're starting to see this become more applicable is in MIMO proposals, which are multi-input, multi-output. So in this example that I found, just a random proposal from the literature, there are 64 parallel antennas, each with its own independent signal processing chain. So of course, what that means is 64 ADCs that all have to fit on one chip. So if you're using a flash ADC, which is the architecture that's used for high speed, the number of comparators necessary on the chip is exponential with the resolution. So you can imagine to implement this proposal with a 12-bit ADC, which is typical for a lot of radios, requires over 250,000 comparators. If we can get a similar performance with a 3-bit, we've reduced that to fewer than 500. So clearly, these MIMO applications motivate a lower resolution ADC device. Another place we see it is in wideband devices. So we're starting to see a transition in the past from IF receivers to zero IF receivers, here denoted direct conversion. And now in the future, even direct sampling receivers, where we don't bother mixing it all and we sample directly at baseband at a really high rate. But to support these extremely high sampling rates, I think people forget that we've got to process the digital data at that high rate as well. So if you're using a 12-bit ADC at some really wide bandwidth, you might have to use a really expensive digital transceiver just to get the data off the chip, not to mention the actual processing that you're going to do with it. But if we can get a similar performance with a 3-bit ADC, it's literally an order of magnitude cost reduction. So clearly there's a cost benefit, especially with these wideband systems that we're seeing more of today. And lastly, the future is trending towards miniaturization. Everybody wants to make things lower cost, lower space, to fit in a nano network or to fit in a increasingly small device. And a lot of times to miniaturize the cost will motivate a low resolution device. In this case, this is a proposal for a low resolution transmitter. But with low resolution comes low performance, right? Everything has a trade-off. So the fundamental idea of my dissertation is how can we squeeze the most performance we can get out of the fewest bits possible? And I hope that the previous slides motivate why we want to go to few bits from a practical standpoint for actual design systems. To address this problem, we looked at a lot of different aspects and wrote a lot of papers over several chapters, but particularly I want to focus on this last chapter, topic I call post-quantization dithering. I think it's the most practical and has the most potent results that should be easiest to interpret. So to start, how do we model an ADC? Since clearly it's at the heart of everything, we need some way to work with it. An ADC is actually a device that does two operations in one thing. So first we have a sampling operation, which I think any of you who have taken DSP are familiar with, where we have some sampling rate that fundamentally limits how well we can represent our data. But what that really is doing is just discretizing the signal in time. In parallel with that, we have a quantization operation, which discretizes the signal in amplitude. They're kind of two sides of the same coin. And likewise, the same way we have a sampling rate in the time domain, we have a resolution in the amplitude domain, which again limits the precision of how we can represent our data. And then finally, we get some binary representation of the signal that goes through whatever DSP we want to operate. So what this quantization step actually does, and what separates it from the sampling step, is that it is a hard, non-invertible, nonlinear operation. So what that means is not only are we losing information, but we're also having a saturation stage where if the amplitude is too large, we're losing even more information. So that's the kind of the distinction here between a linear region where we have this classic staircase function and a saturation region outside that. What makes this difficult in particular is that this transfer function that you're seeing, input versus output voltage, is strictly deterministic. So what that means is all of the classic noise models, which rely on stochasticity or independence with the input, no longer apply in this case because the distortion is a strictly deterministic function of the input. So the noise is highly correlated, and this makes quantization particularly difficult to work. So to get some practical idea of what low resolution does to our signal, consider this classic 12-bit sinusoid. You can see we've got a nice peak in the frequency domain where the power spectrum has the classic, side lobes from the windowing due to the length of the signal. If we quantize it down to 6 bits, it still looks pretty good. I mean, as far as the eye test, you can't really tell the difference in the time domain. But in the frequency domain, we start to see some distortion appear. And where this is really evident is in low resolution. So here at 3 bits, the staircase effect is obvious even just to the naked eye. But in the spectrum, it's clear that we get strong, spurious distortions. What this actually is, because a quantizer, or at least a uniform quantizer, is a symmetric nonlinearity, we get odd harmonics of the input frequency. And those harmonics are so strong that even very high order harmonics alias in throughout the bandwidth of the receiver. So that's why it looks like there's just random spurious distortions everywhere. Those are actually very high order harmonics of the input that alias throughout the spectrum. And this spurious distortion is a problem from a practical standpoint because, like I said, a quantizer is a non-invertible nonlinearity. So you don't know a priori, if you've received this spectrum, whether these distortions are actual signals that you receive at your ADC or if they're just quantization artifacts. There's no way to tell without some other processing. One of the ways that we measure the effect of this is through a metric called SFDR, which is called spurious free dynamic range. This metric comes up a lot. So if there's one place to kind of lock in, it's probably this slide. And basically what it means is just that we take the ratio of the power of the signal we care about to the strongest signal we don't care about. And that is the effective dynamic range of our ADC. So to maximize the SFDR, we want to find a way to minimize these spurious distortions. Where this becomes really practical is when you consider simultaneous transmission of multiple signals. So if you remember, our focus is on wideband devices, where we may receive a lot of signals throughout the spectrum of our receiver at the same time. So in this case, you can see we have a low frequency communication signal with a wide bandwidth and a narrow band transmission at the same time at a higher power, at a different frequency. After quantizing, we not only get the classic harmonic distortion I showed you, but we also get intermodulation products that distort the rest of the spectrum. And more importantly, the harmonics of the high power interferer actually alias into the bandwidth of our desired signal. And that's what you're seeing here, this overlap. And this is a particularly difficult distortion to compensate because it means that there's no way to linearly filter for the quantization effect. Even if you filter all the out-of-band interference, there's still an in-band harmonic that has aliased into and distorted our signal of interest. So you might have saw from the title slide that the word dithering is in the title of my dissertation. So probably it's pretty important. And in fact, we'll see it's one of the fundamental methods in the literature that people try to work with low resolution ADCs. So we'll describe it here. At a fundamental level, dithering just means that you're adding some kind of noise to your signal to try to condition it for the quantization operation. And the distribution of this noise and the temporal correlations are very carefully chosen to try to optimize for some output metric. So the key takeaway is that dithering doesn't change the resolution at the output. It's still 3-bit, it's still the same signal. But by adding the noise, we can try to recover some information about the signal after the quantization, such as typically the conditional moments of the input signal. So why is that important? You can see here for an example demo of dithering. On the left, you see the quantization I showed you before, right? We've got this really bad staircase and lots of harmonic distortion that aliases throughout the spectrum of our signal and really distorts our received signal. With dithering, we're not changing any of the resolution. It's still a 3-bit signal, but we're randomly modulating the levels. So by oversampling, which again, we're cared about wideband ADCs, so we are oversampling, collecting many periods of the sinusoid we care about, we average out the distortion. And by choosing the right dithering signal, this average will converge to a 0 mean error, and the entire ADC becomes asymptotically unbiased. What that means from a practical perspective is that the quantization noise, rather than being very correlated with the input, which you saw as harmonics, becomes spectrally white and uncorrelated with the input. And that's why you see a much clearer spectrum and a much improved SFTR. In this case, the SFTR improves by more than 10 dB. Of course, everything comes with a price. So with this 10 dB SFTR improvement, we've raised the noise floor, which intuitively makes sense. We're adding noise to the signal. So of course the noise floor would increase. And in fact, if you do the math, the noise floor increases about 3 dB if you use the right dithering shape. Where this falls short is in the practical demonstrations where I showed you before. So in this case, by using the effective amount of dithering, we can get rid of the spur. So this in-band harmonic that aliased in and distorted our QPSK signal is now removed, which sounds good. But because the noise floor has to be raised to accommodate dithering, we've lost so much SNR that the data is probably no longer recoverable. So dithering alone is not enough. We need a way to try to recover the signal with an improved SNR, not just reduce the spurious distortion. So now we're going to talk about another area of the literature that I expand upon to address this issue, which are called lookup tables. So a lookup table, and this is a figure from the literature, the kind of classic diagram they always show, is a really simple architecture. You just take a set of previous digital samples that have already been quantized. You concatenate all their binary representations to form an index, and that index addresses a location in memory that replaces the current value. So there's no fancy equations or filtering or anything going on. We're literally just taking all the bits and replacing them with something else. And we do that by looking up a table, right? That's indexed based on the previous outputs. The advantage of this from a design standpoint are that it's really efficient to implement. So at a high sampling rate, you can actually do this with just a 2-level combinational logic. It could be like picosecond delays if you've got the right IC or FPGA. But the challenge is, how do we design the entries in the lookup table, right? It's not enough to just index them efficiently. We need to be able to index the right values. How do we choose those values? At a high level, the reason we want to work with a lookup table, especially for low resolution ADCs, is that we can make sure that the output of the table matches the resolution of the input, which makes this a truly plug-and-play solution. So whatever your digital backend is expecting, if you're throughput limited, in the examples I showed you, you don't have to change the resolution of your signal. You can maintain, let's say, a 3-bit in and a 3-bit out, just drop the lookup table in between to facilitate that transformation. And of course, the extremely low latency makes this especially attractive for wideband devices like high sampling rates, where we can't probably afford to implement a more complex receive algorithm. Even a filter with its multiplications and sums may be too computationally demanding to implement at high rate while in real time streaming the samples. So the first novelty that we developed is a decomposition of the lookup table design problem. Conventionally in the literature, to train the entries of a lookup table, they just treated it as a black box and used some kind of data-driven calibration procedure. So they collected a reference signal, which is a high resolution, and they collected an experimental signal, which is low resolution, and they just tried to reduce the MSE by choosing the lookup table values via like a gradient descent or a numerical optimization algorithm. But this is really non-informative, and it doesn't tell us a lot about how to design lookup tables for new problems, or really what's working under the hood to make them function. So we decompose the lookup table into an estimation stage and a requantization stage. and then further decompose those into an indexing that goes into the estimator and a dithering that goes into the quantizer. So we'll explain what each of these stages mean. But first, we're going to start with the estimator. So to give you a kind of high-level demo of what the lookup table is going to do, we start with a sinusoid, very crisp, beautiful spectrum. After quantization to 3 bits, we get lots of spurious distortions, as I've shown you before. We apply an estimator, which attenuates the distortions by reducing the spur power and amplifies the signal of interest to the appropriate level. And then finally, we re-quantize it with the appropriate level of dithering and store that entry in a lookup table for real-time access. So why did we end up doing that, right? Well, the input to the lookup table is 3-bit, the output is 3-bit, the resolution hasn't changed. Nothing about the system has fundamentally altered the signal, except that the previous one is SFDR limited due to the lack of dithering on the input. After correction, we're noise limited because we've reduced all of the correlations and eliminated spurious distortion. So the actual outcome of the lookup table is a real gain in the SFDR of the signal as compared to the input. And again, all while maintaining the same resolution at the output. To facilitate this, we studied a number of estimation algorithms and compared them for a set of test signals that we think are appropriate. The estimation problem starts with a desired signal for which we have some parametric model. And the parameters kappa are not known a priori, but we have some prior distributions that maybe we believe. And if you don't know anything about them, you just give uniform priors, right? That's typical. We also consider simultaneous in-band or out-of-band interference and some kind of IID dither or arbitrary noise, right? We always have some thermal Gaussian noise at the input. The structure of the lookup table under the hood is to take the previous set of quantized samples, which again are quantized with the noise and the interference included, use them to index an estimator, which produces a high resolution estimate. And then we're going to re-quantize that estimate just to some digital domain that we can work with, some high resolution row. Following that, we can apply a dither and finally output in the appropriate resolution. So this looks very complicated, right? But functionally, it's just a way to design the mapping in a tractable way so that we can use an analytically derived estimator to create a indexable lookup table that's very efficient. So here's where we're going to start to get into some quantitative results. So bear with me here. We have mean square error on the left for a variety of estimators that we're testing in a lookup table. The x-axis here is the order of the lookup table, which is the number of samples that are used to index it. You can see that even with a relatively small lookup table, so a 12-tap filter, right, a 12-order lookup table at the input, we're able to achieve an MSE improvement of over 10 dB.
How many bits?
This is a 3-bit input. Thank you. And likewise for SFDR, the improvement is actually even larger. So compared to no lookup table, we're getting over 20 dB gain in SFDR with this estimator. But what's really interesting is if you compare it to the linear estimator in the purple, the LMMSE is just the optimal linear filter. The mean square error is improved. We get at least 2 dB better, but the SFDR is vastly improved. Again, we have over 20 dB. And the reason is that the structure of a linear filter, or FIR filter in this case, even the optimal one, is not well suited to canceling spurious distortion because it'll have a main lobe around the frequency of interest. And if a spur is near that main lobe, the attenuation will be minimal. But by using a lookup table, we can have an arbitrarily nonlinear estimator. Conventionally, these nonlinear estimators, like the minimum mean square error estimator shown here, would be too computationally demanding to implement at high rate in real time. But by encoding the entries in the lookup table, there's no computation going on at runtime. It's all computed ahead of time at compile time. And that's what makes this feasible at high rate with this real gain over a linear estimator. For an example in a more practical situation, here's the familiar scenario you saw before. We've got a low power communication signal and a simultaneous high power interferer elsewhere in the bandwidth. This is a BPSK, so you can see we've got this nice crisp constellation, no bit errors. After quantizing to 3 bits, the third harmonic of the interferer aliases in band with the BPSK waveform. So even after doing all of our matched filtering, out of band cancellation, and everything that we can to try to recover the bits, the in-band interference fundamentally distorts the signal, and we get over 30% bit error rate on this BPSK waveform. What we can do, though, is by training a lookup table after the fact, we can produce a high-resolution estimate, which is then quantized and dithered to store in the lookup table. That even with a very limited size, in this case, n equals 5 is sufficient, can reduce the bit error rate all the way to 0%. There's actually 3 effects that are revealed in the spectral domain if you look closely. One is that the lookup table is canceling the out-of-band interference very well. The second is that the lookup table is canceling the in-band interference. So even the spur that's right on top of the BPSK is also getting reduced in power. And third, it's amplifying the power in the BPSK waveform that we care about, which previously was lost due to the saturation of the ADC because the interference was so high. This is a very practical situation for a wideband RF device where you're probably going to get lots of different signals with lots of different power, but you only care about one signal with a limited bandwidth. And we can see that a fixed order lookup table can even improve the bit error rate by all the way down to 0% in this case. What's even more interesting is that in order to facilitate the lookup table's implementation, we have to store all of these entries. So a natural question is, what is the memory size necessary? Because to do this in real time, you have to index all of that memory in real time. If we have to index a terabyte in a picosecond, it's not going to happen. And you can see on the right here, even for a fairly large order lookup table, the memory size is really small. In fact, even the highest case is fewer than 10 kilobytes, which is very feasible and practical to index in real time. Another really cool thing about the way we've designed our lookup table approach is that we can even apply estimation in the case of non-stationary interference. So here we have a spectrogram that shows a BPSK waveform that we care about down here at the low frequency and a linear frequency modulated interferer. So LFM is a waveform you might typically see in a radar. So imagine if you have a radar that's close to your receiver and you're also trying to get some communication signal. A wideband device at low resolution will create a harmonic of the interference. And because the interference is non-stationary, the harmonic is also non-stationary, and it sweeps through the signal of interest, sometimes distorting it and sometimes not. And it's a very challenging approach to typically deal with. Now, with a narrowband correction, we can try to cancel one frequency of interest, but it's not really effective. Even though we're canceling the harmonic during the time that it's sweeping through our BPSK, we're not canceling it elsewhere, which is producing a saturation effect that attenuates the signal of interest. In other words, the SNR is too low to recover, even when there isn't a harmonic directly in band with our signal of interest. But with our lookup table, we can actually create a wideband cancellation by updating the prior distribution of the interferer to assume a wider frequency range. By doing that, we not only cancel a lot more of the frequency components across the suite, but we also improve the in-band power of the BPSK, and we get a real SNR improvement across the time range. And all of this can be integrated, again, in real time in fixed point. So the next thing I want to talk about besides the estimation stage is the dithering stage, because dithering, as I've introduced before, is fundamentally a stochastic process. So to do it in a fixed point entry in a lookup table requires some careful treatment of that stochastic behavior. One of the classic questions that comes up is, how much dithering should you use? So in the left case where we have no dithering at all, there's too much distortion due to the spurs that I showed you before. And in the right case where we're using a full dithering effect, there's too much noise, where we sacrifice too much SNR by raising the noise floor to dither.
What does it mean, too much noise?
It just means that there's a lot of noise. So as a designer, you might want a better SNR than dithering can give you. So if the dithering produces an SNR that is not satisfactory, you want to use less noise.
But what's too much? But how much is too much?
Exactly. That's the question. So in each individual application of the lookup table, too much will change. As a designer, you want the ability to choose how much noise is too much and to choose a dither distribution that achieves the right noise level for your application. So with that motivation in mind, is there a way that we can design a dither that trades off between distortion, which is bad for spectral sensing applications? Like I said, these are all artifacts that you can't tell apart, and noise, which is important for communication applications, since it'll limit the bit error rate of our system. So we designed what we call a parametric dithering method, which is where it's effectively a distribution with a variable amplitude. So as a designer, you can choose how much MSE loss you're willing to tolerate in exchange for an equivalent SFDR gain. But the important thing to take away here is that it's a really pretty efficient compromise, right? So even at the worst case, you only lose 3 dB of MSE, and for this sinusoid, you gain 30 dB of SFDR. But in practice, you may want a system that does a spectral sense, where you take a wideband snapshot and see everything that's in your received bandwidth, and then also hone in and demodulate a signal of interest once you've identified it. So you may want to tolerate some distortion if it gives you a better SNR in the communication, but you can't tolerate too much distortion because then you won't be able to identify which of the signal of interest you actually care about. The parametric dither allows us to efficiently trade off between these two options. As a demo here, take a look at our classic sinusoid. We've seen this a few times now. By adding a variable amount of dithering, you can see that the noise floor increases with the more dither amplitude, but the spur power decreases down below the noise floor. Right? And this is not just a case of the noise is overwhelming the spurs, they are actually meeting each other in the middle. So the spurs are getting decreased as the noise floor is raising. So again, as a designer, you choose, kind of pick your poison, how much spur power you're willing to tolerate in exchange for that much noise level increase.
The spurs have some regularity to them.
That's right.
Does that imply that if the dithering puts its energy in different parts of the waveform, you do that more efficiently?
Absolutely. So one of the key ideas is what we call colored dither, which is where we shape the temporal correlation of the dither. So we
You didn't
apply.
pay me to ask that question.
No, it's a good question though. No. So yeah, you're right. And in particular, we see this in audio applications. So high frequencies are less perceptible, so we shape the dither to try to push the correlation in that direction. But even in RF, right, if you know where your signal of interest is likely to be, you can push the correlations away. So that's a good question. Another place we'll see this is we actually were surprised to find it works pretty well in compression applications. So here we have an image quantized all the way down to 2 bits. There's lots of distortion due to the quantization artifacts. With the right amount of dither, you can trade off distortion for noise. And again, here I want to emphasize that the output has the exact same resolution as the input. So the entropy of the system has not changed, which means that the lossless compression rate is exactly the same. But the advantage here is that by dithering, the perceptual quality has improved because we don't have highly correlated quantization noise. The downside is that there's more white noise, and that's where you can see kind of in the background, when you use too much dithering, the background is really highly noisy. It looks very grainy. But without enough dithering, there's very lack of detail on the, for example, the cheekbone, where there's a lot of variation that we want to capture. So as a designer, you can trade this off, and we found that this was really practical for compression. As far as implementing it in a lookup table structure, this is where things get a little more complicated. So previously, I showed you what we call the post-table dithering, where we store a high-resolution estimate, and then we dither it in the digital domain. While this is the best, most authentic form of dithering because it captures all the statistical properties we care about, the downside is that you have to have a higher memory cost to store the estimate in the lookup table, and you also have an increased throughput requirement because in between the dithering and lookup table stages, you have a high-resolution signal that has to go through the digital domain. So these are kind of fundamental trade-offs to this technique. In an effort to mitigate that, the simplest method is just to do what we call intra-table dithering, which is where you hard code the dither into the table and store that entry after it's being dithered. So we apply the estimator in high resolution, we generate a single realization of a dither, and we store that in the table at low resolution. And while this is kind of the brutish, naive approach to implementing dithering, the downside is that by hard coding the realizations, we are losing the stochastic nature of the dither that we care about. We're kind of relying on the stochastic nature to exhibit itself across a wide range of values rather than for a particular value. And as a trade-off in between these two, we've developed what we call intertable dithering, where we hard code a set of dither realizations and store them across a set of tables that we multiplex between. So the idea here is that instead of storing a high resolution estimate and applying a dither, we store several separate dither values that have already been applied and just randomly select between. So functionally, it's a similar approach, but again, the trade-off here is in memory, where to store many lookup tables requires integer multiples of whatever your single lookup table memory size would be. As far as how the dither actually performs with these architectures, you can see here as a baseline, the black line is the SFDR if you didn't use a lookup table at all. And the blue line is the SFDR that I showed you before after we apply our estimation algorithm. Of course, to dither effectively and store it in low resolution, we want to maintain the same output and input. So it's a 3-bit in, we want a 3-bit out. And the dithering allows us to maintain that SFDR even after reducing this high resolution blue line from 8 bits down to 3. In particular, the post-table dithering, as expected, does the best. But like I said, it has those extra trade-offs from an implementation standpoint. But even the inter and intra-table dithering can perform pretty well if you optimize them for that. And the x-axis here, we're just varying the dither amplitude like I showed you. As you might expect, the best SFDR has the highest amplitude, but there's an MSE trade-off.
How much of the bandwidth limitation to such a system comes from the delays in this dithering calculation?
That's a good question. So in practice, it depends on which architecture you use. You usually have a throughput limitation on the digital backend. Like your FPGA can only sample so fast, right? Or your IC, the silicon only handles some digital bandwidth. So that's why the post table is not as effective because you have to do that high resolution, like 3 to 8 bits. So for example, in this case, it would be literally double the digital bandwidth requirement to implement this. But if your system is parallelized or it's less constrained, then yeah, post table is pretty straightforward.
What about analog? 3 bits is analog.
What do you like at the
For
front?
you're doing all these digital calculations for the dithering.
Yeah.
You could do that in analog.
Yeah.
Some
So
occurrence in
yeah.
a common bus, for example.
No, so yeah, in principle you could. The reason we avoid that is because it's again computationally intensive. And as a designer, you've got to implement the dithering.
And then analog processing, which you want to do a dot product in analog, you just sum up currents on a wire and measure it.
Yeah, but the thing is to generate
fast.
the key is that the dither has to be drawn from a very specific distribution. So to generate the dither signal requires typically some parallel digital to analog conversion circuitry just to produce the right dither, especially if we want the properties like you talked about with the correlation. If we want a colored dither with the right spectral shape, we've got to have some complex algorithm to generate that and produce that current before it can be added. And that adds so much cost and overhead that it defeats the whole point of doing things in low resolution anyway. But that's a very good point. Thank you. So as we saw, the estimation and dithering stages can be implemented pretty well, but a fundamental issue we haven't addressed yet in much detail is memory size. A lookup table memory, which is the number of values you have to store in the table, is exponential, both with the resolution and the order of the lookup table. So to try to kind of mitigate this effect, we've designed what we call indexing schemes that are supposed to limit the memory size of the table to become both more efficient and honestly feasible to implement at some real-time addressing space. One of the ways we do that is with what's called bit masking. This is a technique originally proposed in the literature, again, through this black box, numerically data-driven calibration procedure. But here, looks complicated in the diagram, but it's pretty simple. We just throw out some of the bits, right? So if you have 3-bit resolution and you look at the last 10 samples, that's usually 30 bits that form the index to your lookup table. So the lookup table size is 2 to the 30, which is huge. So we just say, we'll take out 15 of those bits, and now the index is only 2 to the 15 is the address space. Of course, the challenge here is which bits do we throw out? We want to capture the information that is most information theoretically valuable to our signal to store in the lookup table. So design of the bit mask is highly non-trivial, and people haven't really developed good ways to do that, especially analytically. I won't spare you all the details. There's a lot of math involved with choosing the right bit mask. But suffice to say, we found an analytical method that chooses a pretty good bit mask and can do so pretty efficiently. And the takeaway here is that under a fixed memory constraint, in this case, 15 bits at the input, if you want to use a classic lookup table like I showed you, your correction is fundamentally limited. Because if you only have enough address space for 2 to the 15 entries, and your resolution is 3 bits, that means you only have 5 samples to work with. And that may not be enough information to cancel the spurs effectively. Here our gain is pretty limited. We only get a few dB with the classic lookup table. With the same memory size, we can look at 10 previous samples and throw out half of the bits. So we get information from more samples, but the information is coarser because we're throwing out some of the resolution. And it turns out that that is extremely valuable to the estimation. It's more valuable to get more samples with less information than fewer samples with more information. And the outcome with the same memory is a significant improvement in the actual gain of the SFTR. Again, under the same constraint memory and still at the same fixed point 3-bit output as the input. From a quantitative standpoint, if you want to look at these results in terms of MSE and SFTR, the bit masking approach under a fixed memory, which is the x-axis, will consistently outperform on both metrics. And it does so by a pretty significant margin. So over a couple dB in MSE, but over 10 dB in SFTR, which is what I showed in the previous slide. And again, this is for a pretty limited lookup table size. You could go well beyond 15 bits at the input and get even better performance if it interested you. What's interesting to point out here is that the performance gain is consistent in that there's no crossovers here. It is always better to use a bit mask. It's just a matter of implementing it prior to indexing the table. So the other technique that we applied is what's called high probability indexing. It's functionally the same as bit masking, but instead of throwing out some of the bits, we just throw out some of the sequences in their entirety. So we bypass the table if we deem the sequence that we've obtained to be of low probability. So kind of the idea here is that we choose, according to some threshold, which sequences are more likely than others, and we only train a lookup table for those sequences. And in that way, we limit the number of sequences the lookup table has to be trained to correct, and therefore the memory size. So as far as quantitative results, the x-axis here is epsilon on the left, which is basically just the size of the lookup, the proportion of sequences the lookup table will correct. It doesn't really matter. It's just analogous to memory. The point is that we can reduce the value of epsilon down to about 0.75, let's say, which means we're only correcting 75% of the sequences that go into the lookup table. The other 25% are bypassed entirely and don't receive any correction. But the actual outcome of that on the SFDR is fewer than 1 dB in loss, which means that the vast majority of sequences don't matter that much to correct because they don't contribute that much to the SFDR. So what happens if we limit the epsilon to take that 1 dB SFDR loss? The actual effective compression ratio is over 4 orders of magnitude. So we've got a lookup table that's 0.01% of the size, but has almost the same exact performance in SFDR. And the penalty is like, half of the MSE improvement. We lose like 5 dB, right? But that's the trade-off you have to make. The takeaway here is that the lookup table space is highly compressible, and that with even a small change in performance, we can get a really huge memory reduction if we choose to bypass the sequences in a smart way. And that's what that whole chapter is dedicated to, is designing the high probability set and choosing which entries to bypass.
Morriel, I have a question. So you're talking about sequences here. So you're taking the memory into account. What kind of signals have you used here for evaluation?
Yeah, that's a really good question. In this case, it's only a sinusoid because a sinusoid is highly compressible, right?
Yeah.
The space is like, if you think about like vector quantization, it's really efficient. In practice, if you care about kind of the idea of our dissertation, is that most signals at wideband look kind of like a sinusoid. So if you imagine any kind of phase shift keying or any linear frequency modulation, all of these typical waveforms at high rate and a small window, which is what the lookup table does, looks tone-like enough. And in fact, large sections of our dissertation are dedicated to seeing how accurate that approximation is, right? Like, can you really treat a BPSK as a tone and under what conditions and so on? So we think that this is representative of some typical use cases, but it remains to be seen how the lookup table performs on like an OFDM waveform, which looks much different.
If you plot the spurs in the waveform, you get a power law?
Yeah.
It sounds from what you have here, you would imply that there are a few that are really important and most aren't.
Yeah. So if you think about SFDR like a min-max problem, only the most potent spurs are the ones that actually matter. And so if you look at like where those are distributed, it's a kind of an intractable problem because of the way the quantizer creates those spurs. But a simple way to think about it is in 1 bit, right? If you have a sinusoid and you quantize it to 1 bit, you just get a square wave. And a square wave is odd harmonics that decay, according to a rational function. So that's kind of one power law. Right, exactly.
Okay. So that's why you get that kind of distribution.
Yeah, there you go. So, we've kind of discussed a lot of different techniques, both for indexing, memory reduction.
Talk about the second.
Yeah, oh yeah, the second plot is the compression ratio. So that's where I was saying that as you change epsilon, which are the different colors, and for the order of the lookup table, you get better and better compression, which makes sense. It's an exponential shape, right? So this is a log. Basically, as the order of the lookup table increases, the compression efficiency improves. And that's where you get several orders of magnitude, even for a very limited table and for a pretty high epsilon. Okay, so where's this going, right? And this is where kind of putting it all together. We've talked about estimation methods to improve the SFDR. We've talked about dithering methods to maintain those properties. We've looked at different resolutions, different indexing schemes, ways to limit the memory size. But as a designer, right, if you're building a chip, you probably don't care about any of that stuff. What you just want to say is, I have this much memory that I can index in real time. How much improvement can I expect from all these approaches amalgamated? So this is that result for mean square error. The x-axis here is the memory size that as a designer you can tolerate. And the y-axis here is the mean square error, where the black line is the baseline, like not using the lookup table at all. And the Pareto front is plotted in red. The important takeaway is that, as an example, if you give me 1.5 kilobytes of memory and a 3-bit signal, I can give you a 9 dB improvement of MSE entirely in the digital domain with no change to anything on the analog front end. And it's a fully post-processing method with O of 1 access time that can be implemented in a 2-level combinational logic for extremely fast access for wideband systems, which is not bad. And again, you can imagine if you give me a megabyte of DDR6 or whatever you can access really, really quickly, or some more efficient approach to get the memory in there, you can get much farther along and much better MSE. We're looking here at really the limited memory domain. On the other side, all of the dithering stuff we talked about was intended to optimize SFTR. So if we re-quantize this signal all the way down to 3 bits, you can give me 324 bytes of memory, and I'll give you 19 dB SFTR improvement with the same resolution as the input. So it's truly a plug and play approach. You can just drop it into your digital signal processing scheme. There's no upgrades necessary on the digital backend to support any higher rate. There's no analog front end changes that are necessary. Through a strictly post-processing high-speed method with basically negligible memory size, I can give you a 19 dB SFTR improvement, which is equivalent to several bits better resolution than we started with. So that's the ultimate conclusion of my work.
Right. The dithering, if you look at it the other way around, encodes part of the signal.
Sure.
So if I had known the dithering signal, I could infer information about the signal. That means the dithering contains information.
Well, yes, once you're in the digital domain. So one of the things people do is called subtractive dithering, where you actually subtract the dither back out once you're in the digital domain. You get an even better estimate.
Right. But because the dither contains information about the signal, you can add and subtract it without adding to the noise.
Yeah. So with
To the
subtractive
extent that
dithering,
it has information.
so functionally, once you quantize, the two are correlated because you're putting on the input and then you quantize it, and the output is going to be influenced. So like I think what you're getting to is this subtractive dithering scheme where you say, well, I know the dither has information, so if I have known information about the dither and I subtract that out, I can get an even better estimate with no noise floor increase. And that's true, but then you have to raise the resolution of your signal. The key issue with the lookup table is what can we do with a fixed point resolution that doesn't change? But yeah, if you can tolerate going from 3 bits all the way to 12 bits in the digital domain, then you can subtract out the dither and do even better. Of course, that comes with its own complications because you need the subtraction to be coherent. So whatever you're doing on one side, you got to do to the other. And you also need it to be anything that, like if the dither is filtered or if anything is happening to it in the analog side, you've got to replicate that for a digital twin to subtract it efficiently. So there's lots of issues that come up with that. But you're right, in principle, that is an area to explore.
So you might want to emphasize the fact why you want to keep the same resolution at the open.
Yeah.
The motivation for them.
So functionally, the whole motivation, and it's in the title of the work, is wideband systems. So if you're working at a really high rate, like you saw from that very first slide, to have a higher resolution digital processing requires an order of magnitude more cost, right? So a lot of times if you're really rate limited or throughput limited, you've got to maintain the same resolution. And moreover, just from a design standpoint, I like the idea of it being plug and play. If you don't change the resolution, you don't have to change anything else that's going on in the back end, and you just drop in the lookup table in between.
But you also study the case when you raise resolution.
Yes, so some of our work is related to the case where you do increase the resolution, which is necessary for things like mean square error, because that's fundamentally limited by the resolution.
There's a technique for ADCs where you add white Gaussian noise to it at half the LSB
Yes,
and get an extra bit.
yes, that's dithering, but instead of using the classic distributions, you use the Gaussian with half LSB as like a good approximation for the right distribution. And there's lots of work on how good is that approximation and how can you play with it. We actually, our whole chapter is dedicated to how to deal with noise like Gaussian on the input. But yeah, that's a very good point.
That's an old technique.
Yeah. Well, people like it because you can just siphon off thermal noise from some other part of the circuit and add it in, right? Like you mentioned, the current summer is very straightforward to put in. But then you got to make sure it's at just the right level. If it's too much,
Half an LSB.
exactly, exactly. So really quickly, I want to go through a couple acknowledgements. This is by no means an exhaustive list, but I think the work that's in here is due to the contribution of a lot of people. So I just want to briefly thank them. First and foremost, my advisor, about whom I could write an entire book about everything that he's contributed to me, but I'll keep it short. I think basically everything I've ever worked on is influenced by his teachings, so I'm very grateful to him. Of course, I'm also very grateful to my committee, who have been very kind and understanding throughout the process and devoted a lot of their time to me, which I really am grateful. I was very fortunate to have 2 different funding sources, one of them being a GA funding through this SCTR program, and one being this National Science Foundation, GRFP. But in particular, I worked with a collaborator named Mike Tinston, and he's been great. He's been really one of the best project managers I've ever worked with. And I'm really grateful to have had him for the entire 6 years that I've worked on this problem.
He's there, you know.
Yeah, he's there. Hope he's hearing me. I also want to thank Dr. Sylvia Kokash-Filipovic, who is here. She was one of the first, well, she co-authored my first undergrad research paper. And I'm really grateful for her guidance early on and for managing me for one of the summers for as an intern. I also want to thank Dean Antoine, who runs the Governor School of Engineering and Technology at Rutgers. He gave me a shot in high school to go to this summer camp where I learned what engineering was. And set me up with a lot of connections to succeed at Rutgers. So I'm very grateful to him. There, I also met Brian Lai, who just recently became a doctor. He defended 2 months before me. He's always been a couple years ahead of me. He's an undergrad at Rutgers in engineering and a PhD student at Michigan. So I really appreciate everything that he's done for me. He's always got some really good wisdom and always very timely, right when I need it. And lastly, I want to thank my good friend Mike Zhao. I did my capstone with him, and I think he's probably heard every single complaint about every project I've ever worked on, and he's always been there for me. So I really appreciate him too. So thank you.
You might want to go to your slide with the work you've done, but you also show all of the work, just to have a reference. Give us a little bit more insight.
Sure.
You mentioned along the way, that table,
Yes, I gotta go all the way back for it. Bear with me.
just to give a scope to the committee and the rest of the people, all the stuff you've done.
Yeah. So like I said, we really only focused on this chapter and a little bit of this chapter for the presentation. But some of the other work that we focused on was anybody who's worked with quantizers has heard of Lloyd Max, which is non-uniform. And all the results I presented for you so far are uniform quantizer. So a non-uniform quantizer is its own whole realm, and we have a whole chapter dedicated to dealing with that through our own dithering method. And as you pointed out, there's also a case of thermal noise. How do we deal with that, which is its own chapter called noisy dithering. And lots of publications along the way.
I probably looked at these different approaches for wideband sensing, or you went into some other domains as well.
So I think the key
Trade
trade-off.
off about some other domains.
Yeah, I mean, so one of the areas we talked about was compression, right? So we did some work on like, how does this affect the entropy of the signal and how does this affect the perceptual quality? But I think the key trade-off that we explored, in large part due to what our funding source cared about, was this trade-off between spectral sensing and communication. Like you want a good wideband snapshot and you want a good demodulator for a narrowband signal. But I'm very open to hearing more.
You said that the quantizer also performs well for image processing.
Yes.
So yeah, we saw it was very good, perceptually good image. How do you measure that distortion?
That's a good question. And it's an open question, right? How do any of these lossy compression algorithms evaluate their image? So one of the popular measures is called SSIM. There's another one, which is like PSNR. These are like image quality metrics. For us, we used a metric called PIQUE, Perceptual Image Quality Evaluator. The underlying details of that are very complicated. I don't want to bore you with it, but functionally, it's supposed to be a referenceless image quality evaluator for perceptual quality. So without having access to the high resolution image, what would a human think looking at this? But yeah, the details of how they compute that are fuzzy. Definitely an open problem in general. How do you evaluate the quality of an image to a human viewer, right, with a metric?
So Morriel has a paper at DCC, which is extremely competitive, if you remember. It's actually organized by one of our Texas A&M professors who likes to ski, so he always organizes in February. It's not really. We met him there when we went to the conference.
Well, he's a source coding.
Source coding person. So that's where he also worked on some image and audio processing. In fact, he's advising a student, right? Undergrad student also.
Oh yeah. Yeah, we're trying to carry on that research as much as we can.
So it looks like also since we last time saw you, since December, you just submitted a couple of journal papers.
That's right. So those are basically, honestly, the bulk of what I presented is those papers. That relates to the decomposition of the lookup table problem, the estimation stage, and the dithering stage.
Okay, any more questions, Mike, Milos? I guess the committee will ask some questions after everybody leaves. We'll have that session. Otherwise,
I can ask some questions.
You want to ask now or you want to ask later?
Okay, whatever. Whatever are the rules.
Up to you.
I can ask now. Okay, I can ask. So I'll have some kind of general question at the beginning. So, okay, you said, does it make sense to maybe look towards like a vector quantization?
Yes. So
but better instead that you are quantized like a set of samples, not one sample, not scalar, okay?
Yeah, yeah. Vector quantization is a very rich field, especially in compression. The key is that we care a lot about ADCs in devices, where vector quantization is pretty much impractical, unless you have some kind of crazy hysteresis or something. So in the context of ADCs, you're pretty much dealing with scalar quantizers. But you're right, in the digital domain, if you're looking at compression, then vector is a field to go.
So the other thing is regarding that lookup table, you said you need some training. Does does can we use some kind of machine learning techniques to do training?
That's a good question.
That will help. Do you have some kind of very weird nonlinearities? Maybe they can help, okay?
Yeah, so the key is, I think the dichotomy we study is all of the literature on lookup table training is data-driven, which is like the machine learning approach. You have a data set and you have some labels, and can the network or some algorithm learn to train the lookup table? The issue with that is that it's subject to the quality of your data set, and it's not very informative. Like if you have a different input signal, you got to retrain the entire network, and we don't know what's going on under the hood, right? You get a set of values at the end, and those are your values. I think the key emphasis of our work is that rather than using these data-driven methods, we have a model-driven lookup table training, where we analytically decompose the problem and independently address each of these stages in an optimal way using actual signal processing. So functionally, bottom line, I think the machine learning approach would probably achieve similar results to us, but would be less informative.
Okay. And also you said you're mainly looking at that broadband transmission, that signals are more or less sinusoidal. And so, but they are very, very often very noisy. So how your method is sensitive to input signal to noise ratio?
That's an excellent question. And I have a whole chapter, well, several parts dedicated to how it performs as a function of the SNR. I have some figures for it. I don't know, I can pull them up now.
Okay. So is there some kind of signal to noise ratio below which does not work or something like that? Or?
Yes. Yeah. If there's too much noise, right, then functionally it's very hard to estimate the underlying input. So your gains are very limited unless you have a really long order. I think one of the key points is the whole performance of the lookup table depends on the order, like how many samples you look at. So you have a lot of noise, you might need to look at 100 samples. And then no matter how much compression techniques you use, the lookup table will not fit in an FPGA. So the more noise, right, the higher order table you need to accommodate it, and it just becomes infeasible from a practical standpoint.
Okay, I will stop here with my questions.
Thank you, Morriel.
Yeah, thanks everyone.
Yeah, so thank you so much for attending. So we'll have to just stick with the committee now.